Let's talk about glycogenesis as well as glycogenolysis and glycogen storage diseases. Now let's start with from the beginning. Let's start with glucose. Glucose can be converted into glucose 6-phosphate. Glucose 6-phosphate can then be converted into glucose 1-phosphate if it is going to continue with glycogenesis, or glucose 6-phosphate can continue with the rest of glycolysis to enter the citric acid cycle and then the electron transport chain to produce energy in the form of ATP. Now glucose 1-phosphate can then be converted to UDP glucose. UDP glucose can then become a unbranched glycogen. This conversion is going to happen with the help of the enzyme glycogen synthase. Now, the unbranched glycogen is just going to have alpha 1,4 bonds because it is going to be just straight. A branching enzyme can take this unbranched glycogen and form a branched glycogen. So a branching enzyme can have alpha 1,6 linkages. Here is an example of alpha 1,6 linkage. Now, a branch glycogen can be converted straight into glucose with the help of the enzyme alpha 1,4 glucosidase. Alpha 1,4 glucosidase. This enzyme is expressed in lysosomes. Now, as you may recall, lysosomes are cellular components that are going to house debris to break down, and sometimes glycogen can be found inside lysosomes. And it is important that lysosomes express alpha 1,4 glucosidase so that they can convert glycogen into glucose. Now, if there is a deficiency in this enzyme, then that will result in a buildup of glycogen, which can result in hepatomegaly due to glycogen being increased within the liver. It can result in hypotonia due to muscles having an increase in glycogen stores. It can also result in cardiomegaly due to an increase in glycogens within the lysosomes found in the heart. This glycogen storage disease is called Pompe disease. It is a type 2 glycogen storage disorder, and as we said, it results in the deficiency in alpha 1,4 glucosidase enzyme. And when this enzyme is not expressed, lysosomes are going to have a increase in glycogen. This will result in hepatomegaly it will result in hypotonia, and it will also result in cardiomegaly. It is important to know that because gluconeogenesis, as well as the rest of glycogenolysis, is not affected, this disorder presents with normal blood glucose levels. It is also important to know that this enzyme deficiency is the only glycogen storage disease that will affect the heart. So the mnemonic Pompe breaks the pump might be used to recall the fact that this enzyme deficiency is the one that affects the heart. Now, this branch glycogen can be broken down with a unbranching enzyme or a debranching enzyme. And this debranching enzyme can be in the form of glycogen phosphorylase. Let's write the name of the enzyme down. So glycogen phosphorylase is going to break down and release glucose 1-phosphate so that it can either be converted to glucose 6-phosphate to then produce glucose, or it can enter glycolysis for ATP production. So glycogen phosphorylase is responsible for the release of glucose 1-phosphate from the glycogen. Glycogen phosphorylase can be used to remove alpha-1,4 bonds until there is going to be 4 glucose molecules left on each side. So here we have 4 glucose molecules on each side, and glycogen phosphorylase can act on glycogen until there's only 4 glucose molecules left on each side. And this is really important because this is called a limit dextrin, and we're going to need even more unbranching enzymes to get the rest of the glucose out. Now, glycogen phosphorylase is important in the conversion of this branch glycogen until there's only a limit dextrin left, which basically means that there's going to be 4 glucose molecules left on each side. And sometimes we can have a glycogen phosphorylase deficiency, and with this deficiency, what can happen is there can be a decrease in glycogen breakdown. As a result, we'll have less ATP, and if there is less ATP, then when someone is exercising, they might have an increase in muscle cramps. They can have an increase in the incidence of rhabdomyolysis. They can also experience muscle weakness as well as exercise intolerance. And because the liver is unaffected, patients who have a deficiency in glycogen phosphorylase will most often have normal blood sugars. So let's also write this down. And this is a glycogen storage disease type 5, known as Mickertls disease. So this is going to result in glycogen phosphorylase deficiency due to a decrease in the breakdown of glycogens. We'll have less ATP, which will result in muscle cramps, which is going to also present with muscle weakness, can have rhabdomyolysis, as well as exercise intolerance. And as we said, because the liver is relatively unaffected, we will have normal blood sugars because we will still have gluconeogenesis functioning. Now, it is important to realize that Pompe disease and Mickertls disease is going to present with normal blood glucose levels. Pompe disease is going to mainly affect the heart, and Mickertls disease is going to affect the muscle primarily. Now, glycogen phosphorylase can then be broken down through a debranching enzyme again until there's only one glucose molecule left on the left side. So this debranching enzyme is basically going to change the location of the glucose molecules until there's only one glucose molecule left on the left side. Now there is going to be another debranching enzyme that is going to cleave this last glucose molecule and release it into the blood. And that is called alpha-1,6 glucosidase. So alpha-1,6 glucosidase is going to be responsible for cleaving that last glucose molecule that's left and release it into the blood for glucose for achieving normal levels of blood sugars. Now this is going to be called Cori disease, and this is a type 3 glycogen storage disease. So let's write this down. This is a Cori disease. And because we're releasing glucose into the blood, and if we have a deficiency in alpha-1,6 glucosidase, what is going to happen is we will have a low blood sugar if you have a deficiency in this enzyme. Now, because there is going to be glycogen being built up within the liver, we will expect hepatomegaly. We will also expect hypotonia due to buildup of glycogen in the muscle. And because we're going to have low blood sugars, we're going to have an increase in gluconeogenesis. And because we have an increase in gluconeogenesis, this can put the patient at a risk for ketoacidosis. Now, the reason why this is going to put the patient at risk for ketoacidosis is because we have an increase in gluconeogenesis. So as you might recall, acetyl-CoA is combined with oxaloacetate to enter the citric acid cycle. Now, if oxaloacetate is needed for gluconeogenesis, If we have an increase in gluconeogenesis, then that means that we are using more oxaloacetate. So we will have a decrease in oxaloacetate levels. Now, because oxaloacetate is needed for acetyl-CoA to enter the citric acid cycle, the acetyl-CoA is going to in turn shift to produce ketone bodies. So it will produce HMG-CoA, which can then produce acetoacetate as well as beta hydroxybutyrate. These are all ketone bodies. So because we have an increase in gluconeogenesis, we will have a decrease in oxaloacetate, and because oxaloacetate is needed for acetyl-CoA to enter the citric acid cycle, the acetyl-CoA is then going to shift to produce ketone bodies instead. Now this unbranched glycogen can then be converted into glucose 1-phosphate. Glucose 1-phosphate can then become glucose 6-phosphate, and glucose 6-phosphate can in turn produce glucose through the enzyme, and this is a very important enzyme called glucose 6-phosphate dehydrogenase. And if we have a deficiency in this enzyme, it is called von Gurke's disease. Let's write this down. Now this step is the last step for both glycogenolysis as well as gluconeogenesis. And if there is a deficiency in this enzyme, then as you might imagine, there will be a hypoglycemic episode for patients who have that deficiency. So that will result in hypoglycemia. Due to liver not being able to release glucose into the blood. The accumulation of hepatic glycogen will result in hepatomegaly. And because the Cori cycle will be defective, patients who have this might have lactic acidosis. So von Gurke disease is due to glucose 6-phosphate dehydrogenase deficiency. Now the reason why there's going to be lactic acidosis is due to muscles producing lactic acid during anaerobic metabolism of glucose. So glucose is going to produce pyruvate, and pyruvate can then become lactic acid through anaerobic metabolism in exercising muscles. And this lactic acid can then go to the liver. So here is the liver. Let's try this lactic acid here. Then lactic acid can enter the gluconeogenic pathway to produce ultimately glucose. If there is a deficiency in glucose 6-phosphate dehydrogenase enzyme, then we won't get this step. And if we don't get that step, then what would happen is we will have a buildup of lactic acid, which can put patients at a risk for lactic acidosis. Now, one thing that we also need to mention is that this glycogen phosphorylase enzyme can be upregulated by the skeletal muscle through calcium as well as AMP. And this should make sense because AMP is released when we have low energy levels, and calcium is used for muscles contractions. And so if the skeletal muscle is contracting, that means we're using our skeletal muscles, and then that tells our body that we need energy. So we can get that energy through glycogenolysis, and so it makes sense that our body is going to upregulate glycogen phosphorylase to give us this glucose 1-phosphate. Then we can use that glucose 1-phosphate for glucose production. The liver is also going to produce CAMP, and CAMP can also upregulate glycogen phosphorylase to give us glucose 1-phosphate.